So students, today I'm going to discuss quickly about the second method of parameter estimation, which is called the maximum likelihood estimation. See, in maximum likelihood estimation, what happens is uh, this is a slightly the setting is slightly probabilistic, as well as as opposed to the probability paper plot, in which we perform linear regression, right? So although we use the quantity, but it was still a very regression oriented approach. Now this maximum likelihood estimation is basically a probabilistic estimation technique. Now suppose we have the measured data as x0, x1 of a random variable, right? And let us say we have the parameter space, which is theta1, theta2, and so on. And theta can be expressed as a vector. Always remember that theta is not random. Now that is the most important assumption of maximum likelihood, is the parameters, the parameters of the distribution are not assumed to be random. They are deterministic. This will not be the case in future when we learn Bayesian estimation. There even theta gets random. That is, your parameters themselves, they become random, right? But here the parameter is not random, right? So what we do is the first question that we ask is, what is the statistical information needed for an estimation problem, right? So as you can see, the data is basically this x0, x1, x2, the n data points. Ideally it forms an n-dimensional data space, right? It's an n-dimensional variable space, because you don't know whether x0 and x1 and x2 or x3 or x4, they have the same distribution or not, right? Now that assumption cannot be made a priori, right? So in general, it's a n-dimensional. So if there are n data points, we have the joint density function that is n-dimensional, right? And of course, it is parameterized by the theta vector. Now the difficulty of this approach is that n-dimensional distributions are very difficult to work with, right? N-dimensional distributions not be statement. So this joint density, as you can see, fx1, x2, x3, xn given theta, now that is very difficult to deal with. So what do? We assume something called the IID sampling, the independent and identically distributed sampling. Now what is the meaning of IID sampling? The meaning of IID sampling is all these sample observations, that is x1, x2, x3, x4, they are independent of each other and they come from the same distribution, right? Which is indeed the case. So if you are, let's say, sampling n values from Gaussian distribution, then ideally x1 should have the same distribution as x2, should have the same distribution as x3, should have the same distribution as x4, although they are the samples from a mother distribution, but they belong to the same distribution, so the distribution should not be different, right? So this assumption is very important, because what happens is, now this n-dimensional PDF, it becomes a product of n marginal PDFs, that is n one-dimensional marginal PDFs, right? So what we do is we make use of independence assumption. Each sample is sampled independently of the others, and each sample belongs to the same parent distribution. So this is what is called as the IID sampling, or independent and identically distributed sampling, right? So once this is applied, this whole thing becomes a product of n univariate marginal densities, right? And each of these marginal densities, they belong to the same distribution. So if x1, x2, x3, these are n value sampled from Gaussian distribution, then fx1 theta will be a Gaussian distribution. Fx2, I mean, given theta is also a Gaussian distribution, and so on. So what we end up getting is a function which is known as the likelihood function. The likelihood function is basically the product of all the marginal densities, right? So product of all the marginal densities. So what is method of maximum likelihood? Method of maximum likelihood maximizing the likelihood function, with respect to the parameter vector theta. So I repeat, it is parameter vector theta. So it means that theta could comprise of many components, 1, 2, or 3. Let's say if it is Gaussian distribution, then theta will comprise of mu and sigma. So what you will have to do is you will have to form the likelihood function and then take the partial derivatives with respect to mu and with respect to sigma square. And then what will you end up getting is you will end up getting the parameters of the distribution. So the maximum likelihood method, the formal statement is the maximum of L theta occurs at a value of theta where dl d theta is 0. Hence, in large number of cases, the maximum likelihood estimate is given of theta, which is theta hat, is given based on the sample observations x1, x2, x3 up till xn, and can be determined from dl d theta is equal to 0. So let us say I have Gaussian distribution with known sigma. Okay. So Gaussian distribution with known sigma. So basically what we want is we want to find out the estimate of mean, that is the estimate of not mean, estimate of mu, right? So here this is given in terms of the vector notation, that is the joint distribution, right? So what you do is first you form the likelihood function, and since it's a product, it becomes easier if you work with log likelihood, that take logarithm on both the sides, because then what happens, your product function, it simplifies to a summation function. Then what do you do is take gradient or basically derivatives with respect to mean on both the sides, and what it simplifies to, your, again sorry I'm saying mean, take gradient with respect to mu. Then what happens is you setting the gradient to 0, it gives mu star is equal to the sample mean, right? That is the estimated value of the parameter mu is actually the sample mean, right? So this is what our maximum likelihood method gives. So the case with unknown mean, and for unknown mean and unknown sigma, what do you have is, again you form the log likelihood function, right? Basically first you form the likelihood function. So you have to assume an underlying distribution, right? This is not a distribution selection problem, this is just a parameter estimation problem. So you have to assume the underlying distribution. Let's say you assume Gaussian distribution for example. So what do you do is you first form the likelihood function, and then you form the log likelihood function, and finally what do you do is you take gradient, or let's say quite simply, we are saying gradient because this is the most general form of mathematical expression for a vector parameters. It simplifies to del of that L, or dl of del mu is equal to 0, dl of del sigma square is equal to 0. Now that gives you two expressions, right? So if you solve these two expressions, what you will see that mu is nothing but mu comes up to be equal to the sample mean, and your sigma comes out to be equal to sample standard deviation. So I ask you to go through this exercise, right? So this is what it is. Your mu comes out to be sample mean, and your sigma square comes out to be the sample variance, right? Or sample standard deviation. So this is what it is. This is in crux what is method of maximum likelihood is, but the method of maximum likelihood will not be clear unless and until we take some examples. And what I will do is probably late in the evening, I will share with you one example on the whiteboard, and that should explain this whole theory very nicely. Because in the lecture class today, I'm going to show you something slightly different, which is Monte Carlo simulation and not a demonstration of maximum likelihood. Okay, so the theory of maximum likelihood is explained here. For demonstrations, that is examples using one or two textbook cases, that will be shown in the lecture in the whiteboard lectures, which will be posted in the evening. So that's all.